Hi folks, welcome to the functions review for the Math SL exams. This isn't an exhaustive review, it's just some of the concepts. It's not produced by the IB, it's just a little review that I made for my class in PEI Canada. To make the most of the presentation, you can download the notes with the link below and print them off. You might want to actually do the work in advance and then kind of treat the presentation as a way to check your work. I want to bring your attention to the fact that there are a lot of different ways generally to solve a problem. So if you have a different way that you've been taught that makes more sense to you, by all means, please do that. Alright, functions. We need to know what domain and range are. So domain is basically the set of all permissible input values, or x values, for a function. It's generally limited by certain illegal operations. Hopefully by now you know you can't divide by 0. Square roots of negative numbers, because we're working within the real number system. Logs of 0 or negatives, and certain values for tangent of theta. Now, we're going to deal with trigonometric functions in a different review, so this is going to be all non-trig stuff. But you should know that wherever cos theta is 0, tan theta doesn't exist, because tan is just sine over cosine. So that means at x values or theta values of pi over 2, 3 pi over 2, etc. Range is just the corresponding set of output values, or typically y values, for a function. So to figure out what that is, having some knowledge of the graph or the asymptotes, maxima and minima, that should help you determine the range. We're going to get to work with some basic functions here, f at x, g at x, and h at x. So if I want g at 5 over 2, that's just telling me to put in 5 over 2 for x in the function g at x. So 4 to the power of 5 over 2, we should know that that means the square root of 4, all to the power of 5. So 2 to the power of 5 would be 32. Let's write that a little nicer. Alright, this notation here you have to be familiar with. It means h following g. So this really means h at g at negative 2. Just like regular expressions, you're going to work from the inside out in your brackets. So we'd need to figure out what g at negative 2 is. And it follows that g at negative 2 is going to be 4 to the power of negative 2, or 1 over 4 squared, or 1 over 16. So h at g at negative 2 means h at 1/16. Okay? H is x squared minus 1. So we'll be looking here at 1/16 squared minus 1. So 1/16 all squared minus 1, which would be the same as 1 over 256. And 1 is 256 over 256. So negative 255 over 256. Okay, inverses. If we want to find the inverse of the function f, that means, first of all, switching x and y. So the function f really meant y equals 2x minus 3. It's a linear function. It's got a y-intercept of negative 3. It's got a slope of 2. If we want the inverse, we switch x and y, so x equals 2y minus 3. Now we'll solve for y, so rewrite it in y equals form. And we get y equals x plus 3 over 2. So that's telling us the inverse of x, of f at x, is x plus 3 all over 2. And if I graph those two lines, I'd see that the first one, the original, f at x, looked kind of like this. And its inverse, over here, would be the mirror image through the diagonal line y equals x. Solve h at x equals 0. So this is different from putting in 0 for x. We're setting h at x, which was x squared minus 1, and setting it to equal 0. So you can say then that x squared equals 1. Remember, when you're taking the square root in an equation, you need to consider both the positive and negative possibilities. Another option here, which would save you from the possibility of missing that -1, would be just to factor x squared minus 1 and call it x plus 1, x minus 1, difference of squares, gives us solutions of -1 and +1. As far as GDC skills go with functions, you need to be able to reproduce a graph from your GDC and show appropriate domain and range. So you need to be able to work with your window settings. You need to be able to show maxima and minima, and your calculator will actually figure out where those max and mins are. Asymptotes and axis intercepts. You also need to be able to solve any equation graphically. We're not going to go into that a great deal right here, but there is a GDC review that I've done that you could check out that skill on. Alright, families of functions. At the very least, you should know these families of functions, probably more than just this, and you should also know your trig functions, which we'll deal with later on. So y equals x is your basic linear function. Slope of 1 passes through the origin. We're talking about families of functions here, so you should be aware that any line basically can be produced from y equals x with some transformations. Y equals x squared, that's a parabola, vertex on the origin. Reciprocal graph, your basic reciprocal graph, is y equals 1 over x, okay, which means it would have the points 1, 1 on it, and -1. -1. You should know that this one has asymptotes. There's the asymptote of x equals 0, or the y-axis. So that would be our vertical asymptote. And our horizontal asymptote is going to be y equals 0, which is the same as the x-axis. Just the equation for the x-axis. Okay, should be aware of what exponential curves look like. So this would be one of them, y equals e to the x. Passes through the point 0, 1. And on this, the x-axis is an asymptote. So it's never going to touch or pass through the x-axis on this basic version of the exponential graph. Okay, y equals ln x is just the inverse of the exponential graph. It passes through the point 1, 0. And on this one, the y-axis is an asymptote. And that's because you can't take the log of 0 or a negative number. So this only exists for positive values for x. Transformations. Okay, so these are general rules that apply for those families of functions and for all functions. For function y equals f at x, the following rules define certain transformations. F at x minus c is a translation of c units to the right. And by the same token, if you had x plus some number, that would shift it to the left. If you have a number tacked on to the end of your function, so f at x plus d, that's going to translate it up d units. By the same token, if it had been minus d, that would move it down. If the whole function is multiplied by a number, that's going to stretch the whole function by a scale factor of whatever the number is in front. So scale factor of p. So this is going to affect sort of the height of your graph, which is sometimes a weird concept because a lot of these graphs keep on going forever upwards and forever downwards. But for a given point, it's going to stretch it vertically. You should note that negative p-values cause a reflection through the x-axis. So anything that used to be above the x-axis will now be below, or if it were below, now it'll be above. Okay, that's what a negative in front of the whole function does. F at q at x, so if you just have your x variable multiplied by some number, produces a horizontal stretch by a factor of 1 over q, the reciprocal of q. Okay, so this kind of affects the width again, might seem strange because you might have a graph that goes forever to the left, forever to the right. It's going to reflect your graph through the y-axis. So anything that was on the right will now show up on the left, or if it was on the left, it'll show up on the right. You should note here that if you had something that was right, a point that was right on the y-axis, if you reflect it through the y-axis, it's still going to be in the exact same place. Just think about putting your hand on a mirror. Your thumb is going to touch, if you're actually touching the mirror, is going to touch the thumb of the person in the mirror. Alright, so let's put this to use, these transformations. Consider the graph of f at x shown below. On the same grid, sketch the graph of -2 f at x plus 3. And there's not supposed to be any change in the color here between those points. So the ones that we know well are this one, and this one. Alright, let's see if we can describe what's happening to this graph. We have a negative out front, which means the whole function has been negativified or multiplied by -1. That causes an x-axis reflection. And we're also multiplying the whole function by 2. That causes a vertical stretch by a factor of 2. I'm just giving shorthand here for how I'd think of it. So times 2. X plus 3, that's going to move our function to the left 3. And this has to happen with every point that's on the graph. So I'm going to do it in blue. This original point right here needs to be flipped through the x-axis, shows up here. It also needs to be stretched by a factor of 2. So right now it has a height sort of -1. I'll double that height, gives it a height of -2. And I also need to move it to the left 3 units. So it should end up right there. I'll undo those steps and just put in the final point. But I would do that in pencil as I go along. Okay, the next point, this one right here, I need to flip it through the x-axis, so now it's 3 units above. I need to double its height, so now it's going to be 6 units tall instead of just 3. And I'm going to move it to the right 3 units. I'll undo those steps and just put the final. Okay, and lastly for this point, I'll flip it through the x-axis. Now it's 3 units below. I'm going to double how far below it is because it's got a vertical stretch factor of 2. And now I'll move it to the left 3 units. Right here. Okay. Finally, I'm going to connect my points. So I have this curved bit to start with, and then the line. Okay, that gives us the general shape. The point A, 3, 1 is on f at x. So here it is, 3, 1. Write the coordinates of the image of A on f at 2x minus 3. Think of what this is doing. The 2x is causing a horizontal stretch by a scale factor of, remember for horizontal stretches, it's going to be the reciprocal of that number, so by a factor of a half, meaning it's kind of half as wide out from the y-axis. And the minus 3, that's going to be a translation down 3. Okay, so I take my points 3, 1. 3 is affected by my width, so it's going to be half as wide out from the y-axis. It used to be 3 units out, so now it'll be 1.5, or 3 over 2. My y value was 1. Now it's going to be down 3 units from 1, or at -2. the function g at x is equal to negative f at x minus 3 plus 1. Give a full geometric description of the transformation from f to g. Alright, so we have to account for all the changes. This negative means that we have an x-axis reflection. So g is the image of f after an x-axis reflection. And we've got this x minus 3. So we're talking about a translation here, or a shift. 3 units to the right. And we have a plus 1 tacked on to the end, which means 1 unit up. The function h at x equals f at 1/3 x. Give a full geometric description of the transformation for f into h. So what's going on here to turn f into h? Well, we've got this 1/3 in front of the x. So h is the image of f after 1/3 beside the x, so we're talking about a stretch, a horizontal stretch. And you need to say a stretch by a factor of, or ideally by a scale factor of 3. Okay, the reciprocal of that 1/3. If you just say after a stretch of 3, well, it's not clear whether we're stretching it by 3 units or making it 3 times as wide. It should be 3 times as wide, so that's why we say by a scale factor of 3. General concepts you need to be real clear about. Y-intercept of a function is going to be here, or here, or here, or here. That's always where x equals 0. The x-intercepts of a function, if they exist, can be found by subbing in 0 for y. So by the same token, if I want to find x-intercepts, wherever we touch the x-axis, we have a y value of 0. Quadratic functions. There's a fair bit of work in the SL course on quadratic functions. They give us parabolae or parabolas. The 3 popular forms to write them in are vertex form. Oh, this is a lovely form. These letters are arbitrary, by the way, so you might have learned different ones. And the IB exams may use different ones as well. So I just happen to use H and K here to represent the vertex in vertex form. So if I had y equals negative 2 x minus 3 squared minus 2, this would tell us that it's opening downwards and it's got a vertex at 3, negative 2. If instead we had x plus 3, well, that would be like subtracting off a negative 3. It would have a vertex at negative 3, negative 2. Okay, if change this to a positive, we'd have positive 2 here. So hopefully you're fairly familiar with those by now. Factored form. Factored form is pretty similar in terms of what the a value does. It tells you the direction of opening and the steepness. So the a value, if it's positive, is going to open up. Your parabola is going to open upwards like this. Or if it's negative, it'll open down. The higher the value of a, the steeper it will be, either up or down. And the lower the value of a, or the absolute value of a, the more sort of fat it's going to be, or less steep. The vertex and axis of symmetry lie halfway in between the x-intercepts, and the x-intercepts are given here as p and q. So if I had y equals 3x minus 5 and x plus 3, this would give us a parabola that opens upwards, that's somewhat steep because it's got a 3 in front, but most importantly that has x-intercepts at 5 and at -3. Okay? And since it has x-intercepts at 5 and -3, 2, 3, 4, 3, 4, 5, and -3, it's going to look kind of like this. Its axis of symmetry is going to be halfway in between those. So the axis of symmetry is going to lie halfway in between -3 and 5, or at x equals 1. That also tells you the x-coordinate of the vertex. And you could just sub in 1 and figure out what the y-coordinate of the vertex is. Not all parabolas can be written in factored form because not all parabolas have x-intercepts. If you have one that opens upwards and has no x-intercepts, we call that positive definite, and one that opens downwards and has no x-intercept would be negative definite. And then some parabolas only have one x-intercept, which means they've got their vertex right on the x-axis. Trinomial form, not really the best form for telling us a lot about the graph at the outset. So we might have y equals a x squared plus bx plus c. This is the general form. C is going to be our y-intercept. That's the nice thing it tells us right away. Again, a determines the direction of opening and generally the steepness. The axis of symmetry is at -b over 2a. That's in your formula booklet. And that also tells you the x-coordinate of your vertex. It can be converted to vertex form by completing the square, by using the axis of symmetry, or using differentiation techniques. It's really up to you. So you have several possibilities here. Often you'll be asked to convert from trinomial form into vertex form. And that's where we're going next. Okay, convert this function into the form y equals -2 x minus p all squared plus q. So we switched up the letters there, but we should still realize that this means vertex form. Meaning that if I knew the coordinates of the vertex, I could just sub them in there for p and q. P would be the x-coordinate, q would be the y-coordinate. Or we can go back to completing the square. So I'll do it by completing the square first. You might have subtle differences in the way you were taught how to complete the square. I'd take out my coefficient here of x squared as a common factor to start with. So if I take out a factor of -2, that gives me x squared minus 3x. I'm going to leave some space here for completing the square. And if I take out a factor of -2 from -11, it'll give me positive 11 over 2. Alright, now I need to take half of the middle term and square it. Half of -3 is easy. It's -3 over 2. Square that. That'll be 9 over 4. The whole idea here is that these three terms form a perfect square trinomial. And as long as you've done half the middle, all squared, then it's always going to work out. So let's factor them. That section that was under red there would give us x minus 3 over 2, all squared. It's going to use the sign of this middle term and always just half of that middle term. Then at the end I have -9 over 4 plus 11 over 2, which would be 22 over 4. Okay, I'm going to combine those terms on the inside, which would give me 13 over 4. And finally, multiply everything by -2. Okay, and that'll give us -13 over 2. Meaning we've got a vertex here at 3 over 2, -13 over 2, or -6.5. Okay, that's one way of doing that, completing the square. Alternately, you could find the axis of symmetry is going to be x equals -b over 2a, which for us would be -6 over 2 times negative 2, or negative 4, gives us 3 over 2. So right here we found the x-coordinate of the vertex. When x equals 3 over 2, we can sub that in for y. Y equals negative 2 times 3 over 2 all squared, plus 6 times 3 over 2 minus 11. Okay, that's going to give us 3 over 2 squared would be 9 over 4. So negative 9 over 2 plus 6 times 3 over 2 is going to give us 9 minus 11, which in turn gives us negative 13 over 2. Okay. So it also gets us to this final form of negative 2x minus 3 over 2 squared minus 13 over 2. As another approach, you could just differentiate and say y prime is negative 4x plus 6. You know that where you're going to have your vertex, you've got a horizontal tangent. So set y prime to be 0. Okay, so 4x equals 6, which means x is 3 over 2. And now we know that when x is 3 over 2, we could find that y is negative 13 over 2 by subbing it into the original. And we're still going to get the same solution, or the same representation. You can take your pick, whatever you prefer. The graph alongside is a parabola with x-intercepts at negative 1 and 5. Oh my gosh, well there's no graph alongside yet, so we better put it in here. And it's important that you have the graph so that you know which way it opens. 1, 2, 3, 4, 5. Great. X-intercepts at 5 and negative 1. And I'm going to give you this graph such that it opens upwards. Okay. So you know that that should look like y equals whatever a is. X, we had an y-intercept here of negative 1. So at negative 1, 0, our graph is cutting the x-axis. So the version of the equation should be x plus 1, x minus 5. For me, it really helps to write it that way before I go talking about what m and n are. So if I have an x plus 1, I must have subtracted off a negative 1. M would be negative 1. And for the n, I've subtracted off a 5. There's a minimum at p negative 36. Okay, so they're asking us, do we know anything about where the vertex is? The minimum has to occur halfway between our x-intercepts of negative 1 and 5. In other words, it needs to occur at 2. So we could say it's the average of our x-intercepts, or a p-value of 2. Hence, find the equation of the parabola, giving your final answer in the form y equals ax squared plus bx plus c. Hold on now, we don't know really enough about our parabola to do that. We've still got that a value to find. Well, given that we've got this, why don't we sub in the other value that we know, namely 2, negative 36. Okay. So for y, I can put in negative 36. For x, I can put in 2. And that's going to give me negative 36 equals a times 3 times negative 3. Or negative 9a equals negative 36, which in turn says that a equals 4. Okay, we're almost there. So really, our equation is this. Let's put it in trinomial form. No big deal. Just expand our binomial. So we'd get x squared minus 5x plus 1x. So minus 4x minus 5. Multiply them out. We get 4x squared minus 16x minus 20. Solving quadratic equations. This will definitely come up somewhere. So for easily factorable equations, factoring's often the best route. So this one here is a nice example. It's got prime numbers on either end. So you know to get a 2x squared, you're going to need a 2x and an x. If I'm going to look for it to work out to have a middle of negative 3x, I can just set it up like this. And I could verify that through distributive property or through FOIL. Zero product property says that if either one of these brackets works out to be 0, the whole thing is 0. Because in a string of multiplication, if you've got one element that's 0, everything is 0. Okay, so that would give us 2x minus 5 equals 0. Move the 5 over, divide by 2. X is 5 over 2. Over here, I'm going to have x equals negative 1 from the equation x plus 1 equals 0. Okay, if they can't be factored, or if you're having trouble factoring them, you can always use the quadratic formula or your GDC. So if we were talking about paper 2 and we saw this question, really I would be inclined to just graph it. Make sure I put it in carefully. X squared plus 1 divided by brackets x plus 1. Okay. My right side is 3. Graph. Find those points of intersection. Looks like there are 2 of them. Second calc. Intersect. First curve, second curve. There's a solution at negative 0.562. And you might want to show a little sketch of your graph to back up your method. There looks like there's another point of intersection around x equals 3. And there we go, 3.562. Or, to 3 sig figs, just 3.56. Okay, now you might be saying, hold on now, that's not exact. I really want to do the exact version. Great. Let's do it then. We could get rid of our x plus 1 on the bottom by multiplying both sides by x plus 1. That'll give us x squared plus 1 equals 3x plus 3. Move it over. Okay, so I'd be looking for numbers here that multiply to negative 2 and add to negative 3. It's never ever going to happen. This is not factorable, or it's not going to happen easily for us. So we should go to the quadratic formula. Nice way of thinking about the quadratic formula is this way, where we've got the discriminant. Or you can put in the b squared minus 4ac. All over 2a. There we go. Now put in our values. So negative b would be 3 plus or minus b squared, that's 9. Minus 4 times 1 times negative 2 all over 2 times 1. Gives us solutions of 3 plus or minus the square root of 17. It's great, we don't have to simplify that because it's prime. Over 2. You should realize that this means 2 different numbers. 3 plus root 17 over 2, and also the solution 3 minus root 17 over 2. And if you actually worked out what those are for decimal approximations, you'd get what we found in our GDC to start with. So you can see how convenient the GDC graphical solution can be. Alright, discriminant. So I talked about it briefly there. Delta equals b squared minus 4ac. So in a quadratic equation, the discriminant tells us how many solutions exist, whether they're 0, 1, or 2. In a quadratic function, the discriminant tells us how many x-intercepts exist, 0, 1, or 2. Now, I know for the case of 1, you might think of it as 2 identical roots. I just find this an easier way to digest it. So if your discriminant is negative, it means that there are no x-intercepts for the graph or no solutions for a single variable equation. If the discriminant is 0, there's one repeated x-intercept or solution. This means that for a graph, you're going to have the vertex right on the x-axis. And if the discriminant is positive, there are two x-intercepts, or two solutions. All right, so the function f at x equals x squared minus 5x plus 2k has no x-intercept. State the possible values of k. Sometimes people get confused here because you've got your x and your k. You should really try and figure out what the question is telling you and what it's asking you for. You want to find the values of k. And it said there are no x-intercepts. So no x-intercepts means that the discriminant is negative. That's likely going to be worth m1, just writing that. Now the discriminant is b squared minus 4 times a times c. And c is 2k in this case. Has to be less than 0. Okay, we'll simplify a little bit. 25 minus 8k is less than 0. Move over our 25. And now we're going to divide by negative 8. Realize when you divide by a negative or multiply by a negative in an inequality, the direction of the inequality changes. And negative 25 divided by negative 8 is the same as positive 25 over 8. Okay, by looking at the graphs of exponential and logarithmic functions, we can see that they're inverses of each other. So I just drew them here. In blue, you've got y equals e to the x. In black, you've got y equals ln x. So those both are talking about a base of e. Y equals e to the x has a horizontal asymptote at y equals 0, so it never crosses the x-axis. Y equals ln x has that vertical asymptote at x equals 0, which is the y-axis. And you can see, just tilt your head to the side, they're mirror images of each other through this line y equals x. We can use that property in finding inverses for exponential functions. And I just thought it might be worthwhile to take the last couple of questions to look at inverses with exponentials. So if I have f at x equals 2 to the 3x minus 5, that really means y equals 2 to the 3x minus 5. If I want the inverse, I'm switching x and y. So no biggie. This is likely worth m1 on your exam. So switch x and y. Now let's try and isolate y. Well, I can bring my 5 over. And now, what can I do? Well, I need to get that y down somehow. What I could do is take the log of each side. And it doesn't matter whether you use natural logs or logs base 10. So I'll use natural logs. Okay. I'm using the golden rule of equations. Whatever I do to one side, I do to the other. I know from my log laws, now I can bring down that 3y, the exponent. I could divide both sides by ln 2. And that'll give me 3y. And I can also divide both sides by 3. So I'll get ln of x plus 5 equals, or rather over 3 ln 2 would be my y. Finally, I can just write it with appropriate notation. And yes, if you'd preferred, you could have put it this way. Using some of your log laws, this is the same as ln 8. Okay. And that would have come if at this stage we had only taken down the y rather than the 3y. You could also have log base 10 here instead of natural logs. All that to say, when you start off with an exponential equation and you find its inverse, we shouldn't be surprised to find a logarithmic equation. Okay, so that holds true in reverse as well. If we start with a logarithmic equation, we should expect an exponential one. So I'm going to assume that you know here that g at x equals ln 2x minus 5 plus 1 is the same as y equals. So let's switch them around. For our inverse, we're going to have to do x equals ln 2y minus 5 plus 1. Before we had to isolate the exponential term. Here we'll isolate the logarithmic term. Alright, there are a bunch of different ways to conceptualize how you're going to move to the next step. My preferred way is to think of ln of 2y minus 5 telling us that we're talking about a base of e here. So if we were to rewrite this in exponential terms, our base of e and our exponent of x minus 1 should give us a result of 2y minus 5. Just like if I were to write log base e of, I don't know, 21 equals x, you'd know that in exponential form that meant e to the x equals 21. Same thing over here. Base is e, the exponent was x minus 1 for us, and the result was 2y minus 5. Alright, now we have to add 5 to both sides. Notice that x minus 1 is up in the exponent, so you can't combine your negative 1 and your 5 as you move it over. Okay, now we can divide both sides by 2, and we get y equals e to the x minus 1 plus 5 all over 2. Or, using our function notation, the inverse of g is e to the x minus 1 plus 5 all over 2. Folks, good luck with your Math SL exams. Tune in for another review.